section 1, we don't do much computation in here. It's just the beginning of us understanding how to interpret graphs. So the name of the section is Graphs and the Stories They Tell, and Introduction to Functions. We'll start talking about how to interpret graphs. So when you look at a graph, we want to look at, well, what does the graph actually look like? Is it increasing? Is it decreasing? What does that mean? Are there labels on the graph? What do the labels tell us? And then how can we take those labels and the shape of the graph to come up with a story that's being told? Okay, that's what the first couple of examples tell us. So graphs give us a picture showing the relationship between two quantities. So there's two axes, your horizontal axis and your vertical axis. Those are the two quantities that we're usually comparing. We can see how graphs change as we travel from left to right. So we read our graphs from left to right, and how they change from one point to the next. We do not always have quantitative graphs, one with a scale on the axis. So sometimes the graphs have numbers on the axes, like tick marks, 1, 2, 3, 4, 5. Sometimes they don't. But whether they do or don't, we can still interpret the graphs. Graphs with numbers are called quantitative graphs. Why can't I write? Okay, there we go. Quantitative graphs have numbers. Graphs without numbers and just words are called qualitative graphs. Okay, so two different types of graphs. In our first example, oh, they've changed the names. So in these examples, like, we make up names and stuff. And then there was this guy named, what was his name? It's like Mike. And we talked about him for like 10 examples in a row. I'm like, what's Mike doing now? But now they've changed names. We have a new person, Yannick. Also, I forgot to show y'all. I said that I was going to show you guys this because I helped on, doing some of the edits for this book. And look, I got a shout out. Hi. Special thanks to me. I'm going to say I wrote the whole book. I didn't, but that's what I'm going to claim. All right. But I did help. We're working on some of this curriculum. And I wasn't expecting them to actually write it in the book. So I was like, oh, wait, that's me. It was nice. All right, back to our actual work. So for problem 1, Yannick rides his bicycle on mountainous terrain to prepare for the annual Tour de France race. Let's assume he's on level ground. So he's riding on level ground, flat surface, and is traveling at a constant rate of speed. So if you look at this graph, it doesn't really have any numbers on it. So we won't be able to calculate exactly what his speed is, but that's okay. But it's constant. So as time travels, he's going to go more and more miles per hour, right? So let's say he's riding, 5 miles per hour. After 1 hour, he's gone 5 miles. What about after 2 hours? 10 miles. After 3 hours, 15 miles. So you can see that there is a relationship between the amount of time that Yannick spends riding and the total distance that he travels, okay? So the qualitative graph for this story has time on the horizontal axis and total distance traveled on the vertical axis. You might also call them X and Y axis, but in our book, we use the terminology horizontal and vertical because sometimes we use different variables instead of X and Y. From this information, we can state his distance traveled depends on the time he has been cycling. So when we have these two quantities, one is going to be an independent variable, one's going to be dependent, we call them. The one that is independent goes on the horizontal axis. So does the time depend on how many miles Yannick has biked? No. Are we like, oh, it's been 5 hours because Yannick biked 2 miles? No. But the distance that he travels does depend on the amount of time that he's biking. So we put the independent variable on the horizontal axis, the dependent variable on the vertical axis, okay? From this information, we can state his distance traveled depends on the time. Yes, and we can see that this graph starts off at 0, 0, and it increases. So how do we interpret this? We want to say as our horizontal axis changes, what's happening to the vertical axis. So as our time increases, this whole graph increases, we can say that the distance traveled increases as well. Remember, we always want to read our graphs, the actual red line there, from left to right. So as we go from left to right, we see that the distance is increasing, okay? We also observe this graph to be linear because it's a straight line. So all of chapter 1 is going to be about linear functions, and then on the other chapters we'll talk about other types of functions. Now we know that Yannick is bicycling at a constant rate or speed. We can say his time increases, or we can say as his time increases, his total distance traveled increases as well, because this line is increasing. All right, we just got all of this information by looking at this one graph. Example 2 is another worked out example, but notice here we have two different line segments, and we have a quantitative graph that has a few numbers. So we know now that if we have a straight line from the last example that indicated that Yannick was traveling at a constant speed. So a constant speed on that graph, on that table, when we relate time and distance, gave us a straight line. Lines can have different slopes or different steepness, right? That's what's going on in problem number 2 here. So what does it mean, or how can we interpret what's going on in problem number 2? It says, describe Yannick's distance covered during his workout. Don't look at the answer there. All right, so we'll go here. What's happening? We see that obviously when he goes 0 miles, his distance is 0. Let me make a better color. Cool. We have this first line segment A. It ends at this point, 1, 20. What does that mean? When the time is 1 hour, the distance traveled is 20 miles. So on this first line segment, he's traveling 20 miles per hour, okay? Then for the second line segment, here, which we're calling B, that's from hours 2 to 4, and between hours 1 to 4. So how many hours does that cover? This is 3 hours. And what distance did he cover? Up here at 40. So he's gone from 20 to 40 miles. So for the first 1 hour, he went 20 miles. And then for the 3 hours after that, hours 2, 3, and 4, he went another 20 miles. Sounds like his speed changed, right? Because he went a lot farther in the first, he went the same distance in 1 hour in the first segment as he did in 3 hours in the second line segment. One thing that we can look at that indicates that there's a change in his speed is the steepness of the line. When we have the steeper line, the red one, it's steeper. That means that we're traveling at a faster speed. So Yannick was traveling at a faster speed. Specifically, he was going 20 miles per hour. And then on the green line segment B, it's a little bit flatter. So that indicates that his speed slowed down over the rest of the hours. All right, so portion A of the graph is steeper than portion B. During part A of the workout, Yannick is bicycling fast and travels a total distance of 20 miles in 1 hour. In part B, he is riding slower and covers the same distance of 20 miles in 3 hours. Based on the labels for each axis, we conclude that a steeper graph indicates a faster speed of travel. And this is in cases where we're looking at time versus distance, because the labels matter. And then now we know also the steepness of the line matters. And then also our tick marks matter, because now we can actually put numbers to these things. Any questions so far? All right, I said I was stopping on time today, so I'll have a couple more minutes. You try. So I'm going to give you a minute to think about these, and then I'll go through and draw out some lines. So it says, sketch a line on each set of axes to match the description provided. In all of these, we have time on our horizontal axis and distance traveled on our vertical axis. Part A says, draw a line to represent Yannick traveling at a slow speed for a short while, then traveling at a fast speed for a longer period. So you should have 2 line segments and think about the steepness of them. Part B says, draw a line to represent Yannick traveling very slowly because he's walking with his bicycle. So if he's traveling slowly, what would the steepness of the line be? And then part C, draw a line representing Yannick traveling very fast. So I gave you guys a minute to think about this one. And draw your little graph. All right, usually I give you more time to work and I will solicit answers. And also there's a way where you can like write also and draw on the whiteboard that we have here to share. So we'll practice things like that in the future. For now, I'll just go through the solutions. For part A, Yannick is traveling at a slow speed for a short while and then travels at a faster speed for a long time. So if he's traveling at a slow speed, that should be a flatter line segment, and it's just for a short period of time. So we'll have a short, flat line segment, and we want to try to make these straight lines. And then he travels at a, why did it change colors? Oops. All right, he travels at a faster speed for a long time. So we want a faster speed, so a steeper line and a longer line. You should have something similar to this. Flat, short line, steep, longer line. All right, do you guys agree? Any questions about that? All right, look at us killing math class today. Only today I'm going to allow silence because we only have 5 minutes left. Going forward, I will insist on somebody talking back to me. All right, part B, draw a line segment to represent Yannick walking very slowly. If he's walking very slowly the whole time, same rate, it would just be a very flat, straight line. And then the last one, Yannick traveling slowly, then fast and slowly again. So he's traveling slowly, then fast. Ooh, sorry. Slow. Then faster should just be a steeper line compared to the slow one. And then that's faster, and then slow again. So this is slow, faster, slow again. So what we should take from just these first 3 problems, when we look at a graph, we want to look at the labels on the graph to determine what 2 quantities we're comparing. And then we want to look at or read the graph from left to right. Is our graph increasing or decreasing? Do we have a constant straight line? And what does that tell us about our outputs? It says as the input increases, what happens to your output? That's the question you want to ask. And then also, when we're looking at distance over time, the steeper the line, the faster the speed. All right, I feel like I can squeeze in one more. So I'm going to squeeze in number 4 and then we'll stop here. Problem number 4, steepness and the stories they tell. We have to fill in the blank here. Use the graph to complete the story describing Yannick's workout. If we look at the graph before we go in here, we see that Yannick starts out with a relatively flat line segment here. So that means he starts off going relatively slow. Then he speeds up and goes faster on his bike. And then, we haven't talked about this one yet, we have a horizontal line. So that means over this entire line segment, over that amount of time, his distance does not change at all. So what does that mean?
It's constant.
Yeah, it's constant. Well, all of them are constant rates, but this one specifically, a horizontal line, means that he's stopped. Right, so when a line's increasing, we know that his distance is changing as time goes on. If the line is horizontal, he has stopped. So filling this in, Yannick begins his warm-up and bikes at a very slow pace, because it's a flatter line, then begins to climb a steep hill and is able to travel faster than his warm-up speed. And after reaching the top of the hill, he stops to adjust his helmet and check his tire. And again, we know that he stopped because the time is going on, but the distance isn't changing. So he's staying in one spot. Right, so starts off slower, then moves faster. Then when we have that horizontal line, comes to a stop. And for the last piece, I always usually put one problem like this on like a quiz and test. So let's be ready for it. Draw the graph to tell the story about Yannick's workout. Yannick travels very fast and then he descends a hill. At the bottom of the hill, he dismounts from his bike and walks back towards, walks backwards on level ground to stretch out his calf muscles. So this one, you have to be very careful with the wording here. We're talking about total distance over time. So whether he's going up a hill or down a hill, his distance is still increasing because he's moving forward. Also, whether he's walking backwards or forwards, the bike is still has distance. When we think about the direction, that doesn't change how much distance we've gone. So if I walk a mile forward and then I walk a mile backwards, does that mean I walked 0 miles? No, I walked 2 miles. So the distance that we're going, or the direction that we're going, doesn't really matter. Keep that in mind. So it says that he starts off very fast as he descends a hill. So his speed is very, very fast, steep, because you're going down a hill, so you're going fast. And then he dismounts from his bike and walks backwards on level ground to stretch out his calves. So he dismounts and walks. Well, walking is probably going to be way slower. That's it. Did I miss one? Yeah, that's it. So we just have those two segments. He's going down the hill really, really fast. Even though he's going down, his distance is still increasing. So that's an increasing line that's very steep. And then he starts walking slowly. So that's still an increasing line because his distance is going up, but he's going slowly. So it's a flatter line. So here, this example's already worked out for us. So we can see, if we look at the graph, I'll kind of trace it along. We start at 0, 0. And then as the time increases, the speed is increasing all over segment A. And so we get to this point, and then on line segment B, the speed is exactly the same. It's remaining constant. And then on line segment C, the speed is decreasing. So what does this mean? How can we really interpret this? It's saying that Yannick is still biking. Over that first segment of time for line segment A, he's increasing his speed. And that would make sense. If you start off riding a bike, you start at no speed, and then you pick up speed for a while, and then you determine like what speed you want to cruise at for a while. So that's what's happening at B. He finds a speed that he likes, rides at that same exact speed for a while, and then eventually he's gonna have to stop. So over line segment C, he's taking his time to slow down and eventually comes to a stop. All right. On to problem 6. New labels on the axis tell different stories. All right, so Yannick's bicycling workout on flat ground. Use Yannick's bicycling workout on flat ground to draw the appropriate graph for each story below. And for all of these, we're looking at the speed over time, okay? As time increases, Yannick's speed increases. So if he starts off at 0, as the time goes up, his speed is going to continue to go up. Okay, that's just an increasing line. For part B, Yannick is cycling at a very fast and constant speed for a while, then suddenly suddenly slows, but does not stop. Okay, so it's saying that his speed is starting off fast and constant. Okay, so if it's starting off fast, we're not starting off at a speed of 0, we're starting somewhere up here. And if he's riding at a constant speed for a while, that means he's maintaining this same speed over a long amount of time. And then it says he steadily starts to slow down, but he doesn't stop. So we have a line segment that's horizontal, and then we should have a decreasing line segment to indicate the speed is slowing down. But he never stops, so we don't want that line segment to go all the way down to the x-axis or the horizontal axis, because that would mean that the speed is 0. We just want it to decrease. All right, and then for part C, Yannick is walking his bike at a constant speed towards his car. Okay. It just says he's walking the bike. That's probably going to be a little lower than if he was riding really fast. And it's at a constant speed towards his car. Doesn't matter which way he's going. If he's walking at a constant speed, we're going to have a horizontal line. The speed is not changing. All right. So pay attention when you have graphs like this to how the graph is labeled, because if this were labeled distance over time, then the way that we interpret these increasing lines, horizontal lines, and decreasing lines would be totally different.
I have a question.
Yeah.
So for number B, why did I know how you put where the dot is, it's farther up, but for number C, you didn't. So why did you put the line where it was for C, but for B, you put it higher up? Like why? How did you know to put it?
What's the difference between B and C? What does the one being higher up represent?
Well, he's higher. In B, he's going So I guess because this is faster, you would just put it a little bit higher up, and then for C, you just leave it somewhere below.
Exactly. And this is not a quantitative graph that has exact numbers. So I can't exactly say how fast we're going or slow, but if we're comparing B and C, yes. If we're told in one that he's going very fast and in the other that he's walking the bike, the graph in B should start up a little bit higher just because he's going faster. Good question.
Okay, thank you.
You're welcome. Any other questions? All right, so let's go on. Oh, wait, let's not go on. Let's do part D. Okay, so then part D here, it says, is sitting in a movie theater waiting for a movie to begin. Create a story using the graph below. So I want you guys to take a moment to think about this. We're looking at the distance from your seat over time. So this is showing a few different line segments. A, B, C, D, E, F. So think about what it would mean for us to have an increasing line that's going away from the seat, or a decreasing line is going back towards the seat. What does it mean when we have these horizontal line segments? And I'll put that all together to tell a story. So your story should have an explanation for each one of these line segments. So at least 6 different parts, okay? And you can add as much fluff as you want to. It's really not necessary. But you can say something like, she left her seat to go to the concession stand, then realized that, she left her wallet. So she went back to her seat, stopped to find her wallet, then went back to the concession stand, waited in line for her snacks, and then went back to her seat. Something like that. And that's the situation that would match up here. Or if it's not the concession stand, the bathroom. Okay. So the point is, this person left, came back quickly. So left and immediately turned around, stayed at the seat for a little bit, then went farther away, stayed there for a while, and then eventually came back to her seat. Okay. Let's write this out. All right. Which is Lane. Okay, whatever the name is. Left her seat to head to the bathroom. Sure, we'll go to the bathroom or restroom. So that's the first line segment. She turns back to get her bag from her seat. So that's part B, going back towards the seat. She stops to get the bag. Then heads back towards the restroom. All right, so just to be a little thorough here, this would match up with segment A, this would match up with segment B, this would match up with segment C, and then segment D. So now we're in part E, this long horizontal line. So the distance from her seat isn't changing. That would be while she's in the bathroom. So maybe there's a line in the bathroom, so she has to wait, and then, wash her hands, eventually come back. So part E. She waits in a line, then uses the restroom and returns to her seat. Returning to her seat, that would be the part F. All right. So again, when you have problems like this, or you have to tell the story, I'm not going to be grading you on how interesting your story is. don't really care much about that, but it'll be fun to read interesting ones if you want to make it interesting. I'm more looking for you understanding that the increasing line means that she's going away from the seat. The decreasing line means she's coming towards the seat. The horizontal lines represent times where the distance isn't changing. So for part C, she's at the seat for that small amount of time. For part E, she's in the restroom for that amount of time. And then again, we have that decreasing line that's going back towards the seat. All right. Moving on to problem number 7, where we have a quantitative graph, a graph with some numbers. This one's already worked out for us, so we can read through it really quickly. Spiro's new company tracked their profit margin during their first 6 years of operations. What story does the graph below tell in regards to Spiro's profit? Okay, so if we look at what's happening, the profit starts off in the first year at negative 100,000. So he's starting off in debt. Okay, so that makes sense though, because when you start a company, you have to put money into the company before it starts making money. Okay, so Spiro invests $100,000 in his startup company. And then over the first year, it looks like he earned enough money. So he earns some money in the first year, so that now his profit is at 0. So basically he earned the money back. If you're at 0 profit, that means that the money that you spent is the same as the money that you earned. So right, he earns his money back over the first year. Over the second year, his profit doesn't change. Okay, so during year 2, no profit was made. And then if we look at what's happening on the next line segment, from years 2 to 4, so in the 3rd and 4th year, life's great. He earns $100,000 in profit each year. For the 3rd year, he earns 100,000. And then in the 4th year, he earns another 100,000. So now he's at 200,000. Okay. And then over years 5 and 6, he earns $150,000 per year and ends up after 6 years having a profit of $500,000. When we have quantitative graphs, this is nice because we can be more detailed with our descriptions. Instead of just saying, oh, the profit increased or the profit decreased, we can say exactly about how much it increased each year. All right, 7 was done for us. In problem 8, we get to try. Each of the graphs below describes a family trip driving from home to the Navesink Twin Lights Lighthouse that was constructed in 1862 and is now a U.S. National Historic Landmark in Highlands, New Jersey. Fascinating. We should go visit that sometime. All right, the distance from home measured in miles depends on the time. So this is a distance over time graph. And the time is measured in minutes. Note that the time is on the horizontal axis and the distance is on the vertical axis. We want to match each description with the graph. So let's see. We're gonna have to do this one at a time. So we'll read the description and then determine which graph matches with the description. Okay, for the first one, it says Abdul's family is 10 miles from home and drives 5 miles in 10 minutes when returning home. So when we look at these graphs, 2 things we can do. First, look for the ones that start off 10 miles from home, because it says that Abdul's family was 10 miles from home. All right, so we can eliminate graph 2, graph 3, graph 5. We've narrowed it down to either graph 1 or graph 4, okay? Graph 1 starts off 10 miles from home. And graph 4 starts off 10 miles from home. All right, so that's good. What else are we told? We are told that he's 10 miles from home, check, and he drives 5 miles in 10 minutes when returning home. So between graphs, let's see if I can get them both up here. Between graphs 1 and 4, which one do you think would match up with part A in Abdul's situation? It would be graph 4. Graph 1 is going further away from home, so that wouldn't work. But then also let's make sure that graph 4 makes sense. It says we start off 10 miles away, and then after 5 minutes, after 10 minutes, we are 5 miles away. that matches up. It says that we drove 5 miles in 10 minutes. So that matches up with what we have. All right, on to part B. Samantha's family leaves home and drives 10 miles to arrive at the lighthouse in 25 minutes. All right, so looking at these graphs, if Samantha's family is leaving from home, which one of these graphs do you think it would match up with? Graph 2, because graph 2 is the one that's starting off at home at 0, 0. Let's make sure the rest of the stuff matches up also. After 25 minutes, we've gone 10 miles, so that matches up. For part C, Mindy's family is 10 miles from home and drives 5 miles in 15 minutes towards the lighthouse. Okay, so which picture or which graph does this match with? All right, so this was, C, and that matches with graph 1. Part D, Andrew's family is 5 miles from home and drives 5 miles in 20 minutes towards the lighthouse. We start off 5 miles from home, and then it says in 20 minutes, we go another 5 miles. So yes, after 20 minutes, we're at now 10 miles. So that matches up. This was part D. Graph 5, and last one, we have to make sure it matches. Aaron's family car had a flat tire. Oh, sad story. 5 miles away from home and never arrived at the lighthouse. So yeah, that would just be this here. Them stuck 5 miles away from home with a flat tire. Then let's move on to problem 9. This one's done for us, and this is just an example of a non-linear story that might be told. Yannick is at the starting line of his bicycle race. When he begins to pedal from a stopped position, he initially travels very slowly, but then his speed increases rapidly until he is cycling very fast. So if we look at his time over distance, the distance that he travels every minute is not going to be the same because he's going faster and faster and faster. So in the second minute, he's traveling faster than he traveled in the first minute. That means the distance that he travels in the second minute is going to be fast or more than the distance that he travels in the first minute. So in this case, when we're looking at the distance over time, the speed is not constant. So we don't end up with a straight line. The speed is constantly increasing. So we end up with this curve that is increasing. Okay, so this is an example of when you would have something that's nonlinear. When you're looking at distance over time, but the speed is not constant, then you don't get a straight line, you get a curve. All right, number 10 gives us 2 other curves, and we have to kind of interpret what's going on in these situations. 10A, we're looking at the temperature of hot cocoa over time. It says create a story about a cup of hot chocolate in an ice hotel where the temperature is maintained at 25 degrees Fahrenheit. So if you make a cup of hot chocolate, of course, it comes out very, very hot. It's in the name. But then if you leave a hot drink sitting out, what happens to it over time? It eventually cools off. But does it cool off forever? No, it doesn't cool off forever. Is it going to end up like, you know, you leave your coffee sitting on your desk, does it turn into like a ball or ice rock of coffee? It doesn't freeze over. It eventually gets to what temperature? The temperature of the surrounding area, or room temperature, we would say. So that's what's going on here. This cup of coffee starts off really hot, then it quickly decreases because it's in an ice hotel. And then eventually the cup of coffee is going to cool until it reaches the room temperature, which is 25 degrees Fahrenheit. So we'll say, is it coffee? Oh no, it's hot chocolate. So the cup of hot chocolate starts off very hot, then cools down until it reaches the room temperature. And here we're told that that's 25 degrees Fahrenheit. So it cools down until it gets to 25 degrees. All right, in part B, we're looking at the temperature of a smoothie over time. Now this is the opposite. If you get a smoothie, Your frozen smoothie starts off very, very cold, but then if you sit it in a regular room, what happens? The temperature of the smoothie is going to increase over time, and it's going to keep increasing until it reaches room temperature. So same thing here, except now instead of decreasing, we're increasing. The smoothie starts off very cold, and, or I'll say then warms up. As time goes on, I'll just say it warms up as it sits out. We're not given the exact temperature of the day, so we can't say exactly what it warms up to, but we'll know it'll get warmer.